Hi, in today's video, I'm going to be talking about basically a Lorentz transformation of a tensor, second rank, and we're going to consider this case or proof, or showing it, not really proof. If your second rank tensor, like the normal, space-time, four-dimensional stuff, so 16 entries, if your tensor is symmetric, prove that if you do a Lorentz transformation, or show, it is also a symmetric tensor in the new coordinates, so after a Lorentz transformation. And the trick we're going to be using is we're going to consider the components of the transformation, or the hint, the components of the tensor, not transformation, the components of the tensor in the new frame or the new system transform as products of four vectors that are transformed, basically. And that's basically like saying, you can consider, if you wrote 1, 0, you're basically saying, this means not basically. I'm hypothetically saying that's the same thing as this. It's not, but you can consider it, because it turns out being the transformation under a Lorentz transformation, like the standard configuration, whatever that be, and special relativity, whatever that is, Lorentz transformation, the standard one, that's the same thing as saying a prime 1, 0 is going to look like product of the primed 1 and 0. So I could either leave it like this or just say, oh, I'm going to treat them different, expand out how these transform individually. So these are four vectors in themselves. We know how they transform under a Lorentz transformation. And then what you do is you expand it out, and then everywhere you see now, later on, you'll see something like a 0, 0. You want to write a 0, 0. And that gives you a little hint, or like cheat, to figure out how components of the tensor transform under a Lorentz transformation. Okay. So with all that in mind, so how would you go about solving this problem? And the standard transformation I'm going to be using is this, and this is how the components transform. The typical normal thing. So I have gamma 0 minus beta 1 prime 1 is equal to gamma 1 minus a beta is 0, and then these stay the same. Okay, so with this in mind, all you do is prove or show you want to first figure out how do they transform, and then you're going to show, or you could do it at the same time, simultaneously. You could show that they're symmetric, and the symmetric case, the symmetric definition that you need to satisfy is, if you had a tensor, the indices, if you swap them, they're the same. So we're going to assume this is true in the original coordinates, so without the primes, so like these guys. But we want to show this holds, we want to show in the prime system, the tensor after a transformation, when A and when J and I look very similar, we're going to show this holds. Okay. And another thing to consider, because it's a second rank tensor and it's four vector stuff, it ends up being, your tensor looks something like this. And symmetric, it means if you swap indices, they're the same. So we don't have to consider along the diagonal, because diagonal entries are symmetric to each other. like themselves. So if you swap, it'd be the same. So 4 minus 16, because it's 4 by 4, is 12. So there's 6 here and 6 here. And what you'll see is, since your transformation looks like this, the standard one, I'm not doing the general one, you only have to check double product indices, or two indices that look like this, with this and this. So this product gives you 0, 1, or 1, 0, and one of these, and this one with one of these. And you do back and forth, and back and forth, the arrow means 0, 1, and 1, 0, or 1, 2, and 2, 1. And you'll see, you don't have to do A1 with A3 because it's the same as doing A2. It's symmetric, or it's without loss of generality with respect to this and this. So I don't really need this 3, but I wrote it because you need to know if this wasn't how it changed. If these weren't the same, then you need to do it. So we only need to check 1 pair, 2 pair, and then 3 pair. So that means we only have to check, out of the 12 we don't know, we only have to check 6 of them, or calculate 6, which is the same as calculating 1, 2, 3 on this side out of the 6 possible. Right? Yes. Okay. So assuming this is true, let's do it for 1, 0. And like I said, they transform like product of two Vor vector components. So prime 1, 0, what is that equal to? So I multiply this by this. That's how it's going to transform. That's how it looks like. Right? So your gamma squared. This one's going first. So A1, 0. A1 times A1 by minus beta. 1, and then this times this minus beta. 0, 0. Plus beta squared. 0, 1. This is symmetric. This index is the same, not symmetric, same because of the symmetric property. So I could erase it and do, I could write it as 1 plus, you don't have to, but I'll do it. You can write it as this. It simplifies with this term, but you don't have to do it. You just want to prove it's symmetric. Right? Okay. So you get that. Prime 1, 0. So that is what that is, right? So now we need to check for prime 0, 1. Okay, so that's the same thing as this one multiplied first times this one. And because we didn't really change anything, you could just swap the indices with each other. That's only because they appear symmetric with each other. So, but if you did it with these two, you couldn't do that. So you'd have to multiply it out if you wanted to be safe. But you're gonna get this 0, get the same 0, 1 minus beta 0, 0 minus beta 1, 1, and then you get this term times this term. And you'll see the 1, 0 is the same thing as 0, 1, just like this term, and you end up getting, and it was a plus because it's minus, minus. So you end up getting the same thing. So yes, one of these is good. And we did this, and this. So now we're going to do, I guess, this one and this one. Right? So let's do it. 0, 2. What is 0, 2? Transforms like products. So I do this one times this one. So gamma A0, 0, 2 minus beta 1, 2. A prime 2, 0 product. So this one times this one. 2, 0 minus beta 2, 1. Since they're symmetric, since this is symmetric, indices are the same as 0, 2, 1, 2, and they are the same, as you can see. Okay, so, and trivially, I don't have to do it, but you can do it for fun. This last pair, it turns out it is the same thing we just did with this one. Not the same, but like same calculations, okay? So you end up getting, you end up knowing, you know, for all I and j. And I and j go from 0 to 3, right? I should say, we know A prime ij for all ij. And Iij is equal to A prime ji. So under a Lorentz transformation, right? The tensor stays symmetric, or keeps its symmetric property, aka this holds. If this will hold if we know it's symmetric in the original coordinates, right? And we're using a Lorentz transformation. Okay, so that's about it for this video. You could also do this for, you could also do the exact same procedure like with, you wanted to prove what's the opposite of symmetric? You say anti-symmetric or anti-symmetric. So that's the same thing as saying and ay ay ay. So if this holds and this holds, we have anti-symmetric. So you can show if this is the case and that, which is the same as anti-symmetric, in the original coordinate system, we can prove or show that if you consider a Lorentz transformation in this way, the same way, or a more general version too you could do, but this is easy, simple calculations because you can always choose a frame such that this, right? And then it ends up being, if you do the same calculations, if you treat them like products of 4 vectors, is how they transform. You simply just do the same calculations of these multiplied by each other in the new frame, and then you end up getting that it is true. If you have an anti-symmetric tensor of rank 2 under a Lorentz transformation, you will get a anti-symmetric tensor of rank 2. And it's for, 4 vectors, like 4 dimensions, 4 components, right? So basically I'm saying that the I and j go from 0 to 3. Yep, so that's about it.